Yes, good evening, friends. So, today we are going to see the concept that is what isomerism. So, what exactly the isomerism? Isomerism means what? The compounds having the same molecular formula, the same molecular formula, the same molecular formula, but different structural, different structural arrangement, different structural arrangement. So, this phenomenon is called as the isomerism. Now, here in inorganic chemistry, this isomerism can be classified into two ways, or it can be classified into two types. It can be classified into two types. The very first type is what? It is structural isomerism. The very first type is what? It is the structural isomerism. The structural isomerism. And the second type, that is called as stereoisomerism. The second type is called as stereoisomerism. Now again, this structural isomerism, it will get classified into six parts. It will get classified into six parts. So the first one is, that is ionization isomerism. Ionization isomerism. The B is hydrate, or what we can call it as, it is also called as what? Solvent isomerism. The C part is the coordinate isomerism. The D one is linkage, or we can call it as what? Ambidentate isomerism is called as what? Ambidentate isomerism. And the E part is polymerization isomerism, and F part is positional isomerism, and the positional isomerism. So under stereoisomerism, it will get classified into the two parts. The first one is what? Geometrical isomerism, and the B part, that is optical isomerism. So this is what the broad classification of what? Isomerism. Now we'll first discuss about the stereoisomerism, under which we are going to see the very first is geometrical isomerism. Okay, so the first one is, that is geometrical isomerism. Now in geometrical isomerism, it again shows the two types. The first one is cis isomerism, and the second type is what? It is trans isomerism. Okay, now the condition for cis isomerism is what? The same groups should be at 90 degrees to each other, whereas in trans isomerism, the same group should be should be at 180 degree to each other, at 180 degree to each other. Okay, so that is very important. So these are what the basic conditions in case of what, the geometrical isomerism. Okay, geometrical isomerism. Okay, so we are going to discuss about the three important substances, geometries, that is the tetrahedral geometry, square planar geometry, and the octahedral geometry. So first we'll discuss about the geometrical isomerism in accordance with the tetrahedral geometry, square planar, and octahedral. Okay, so let us start with geometrical isomerism for tetrahedral, square planar, and octahedral. Okay, octahedral. So let us start with the things. Now the first one is we are going to discuss about the tetrahedral. The symbolic representation for tetrahedral is what? It is TD. If I'll draw the diagram like this one, suppose if I can take the example, that is M A2 B2. Now M is what? It is my metal, A is the ligand, B is also the ligand, but especially it is what? The monodentate ligand. So how the tetrahedral molecule look like? It look like this one. So this is A ligand, this is A ligand, B ligand, and B ligand. Now see here, in this case, it does not show any kind of cis or trans isomerism. So what I can say that no cis and trans, no cis and trans are possible for the tetrahedral. Why? Because the condition for geometrical isomerism, so as to show the cis is, are the same groups are 90 degree to each other. Now if you see the bond angle in tetrahedral, it is 109 degree. Okay, so definitely it does not show the cis as well as trans. For trans, the same groups that should be 180 degree to each other. Okay, so no cis and trans, that means zero geometrical isomer. Now the second class of compound is square planar complex. Now suppose, for example, we can take example Ma2 B2. So again A and B, these are what? The two monodentate ligands. So suppose if I'll draw the diagram like this one, this is metal at the center. Okay, now see A and A, suppose this is A, this is A. Now the B is like this one, B and B. So definitely what I can say that the opposite groups are at what? 180 degree. The opposite groups are at 180 degree. Similarly for A ligand. So they are what? 180. So definitely this is what my trans isomer. Definitely this is what my trans isomer. Now the second thing that I am going to show it here is it has the cis isomers also possible. See, cis isomers is also possible for this one. How? This is my A, this is A. Okay, so the bond angle is what? It is what? 90 degrees. So B, this bond angle is what? It is 90 degrees. So definitely square planar shows the cis and trans isomers. So ultimately it has the geometrical isomer. Now the next one is that is the third class of compound is octahedral complex. Now let's take example, that is M A4 B2. Okay, so I can show like this one. This is metal. Okay, so if this is what the axial position B and B, they are opposite to each other. This is what 180, this is AA, and this is what my AA. So these are what the opposite groups. These are what the opposite groups, AA, and this is what my B. So this is what my trans. Similarly, I can compose the next isomer, that is the cis isomer, that is M cis isomer. So if this is what my B, adjacent the position of this B is what, if I'll going to take another B here, so the this bond angle is what, it becomes 90 degree. So similarly we'll go in this way. So this is A bond angle 90 degree. Now the next one is, this is A, this is A, the bond angle is what, 90 degree. So this is what my cis isomers. Okay, so this is all about the geometrical isomerism. Okay, we'll see the details in the next part. Okay, thank you.